Okay, so we're going to look at this example. Um, how do we calculate the pH of a buffer? And also, how do we calculate the pH of a buffer after adding a certain amount of acid or base? In this case, it's a base being added. So let me just go through this question, um, which is in two parts. The first part says calculate the pH of a 0.30 m ammonia solution and a 0.36 m ammonium chloride buffer system. All right. So that's the first part. And then the second part is asking what is the pH after the addition of 20 mils of a 0.050 m sodium hydroxide to 80.0 mils of the buffer solution. Okay. So the first part is to calculate the pH before the addition of the sodium hydroxide and then after the addition of the sodium hydroxide to 80 mils of the solution. And what we're going to see is the fact that the pH will not change much. All right. So what I'm going to do is get out of this and go to my writing smooth draw application here. And I'm going to start by doing the first part. So for the first part, what we're going to use is the Henderson-Hasselbalch equation, which as you should recall is pH is equal to pKa plus log of the concentration of the acid Okay, so I'm back in business here. Let me erase this here and go back to my pencil here. Okay, so as I was saying, concentration of the acid divided by, actually this should be the base, concentration of the base up top. And in fact, let me even go further and include what the actual base is. The actual base is ammonia, NH3 divided by the concentration of the acid, which is NH4 plus, all right? So all we have to do is plug the numbers in. But before we do that, we need to find out what the pKa of the ammonium ion is, right? Now, if you look in the tables, you won't see that. Instead, you'll see that Kb for the ammonia is 1.8 times 10 to the minus 5, all right? So Ka for the acid will be equal to Kw divided by Kb, which is equal to, and you know what? Let me make sure that I'm telling you the right thing because I have a sneaking suspicion that I could be wrong. Let me go to the tables here. Files, tables, and let me look for dissociation constants. Okay, so for ammonia, yes, I was right. Okay, so Kb for ammonia is 1.8 times 10 to the minus 5. So let me go back to here. So therefore, I can find Ka, which in this case will be equal to 1.00 times 10 to the minus 14 divided by 1.8 times 10 to the minus 5. And when I worked that out, I got, actually, I didn't do it that way. But anyway, let me work this out right now. So 1 times 10 to the minus 14 divided by 1.8 times 10 to the minus 5. So I got 5.5, 5.6 times 10 to the minus 10, which means that pKa is equal to minus log of that same number, 5.6 times 10 to the minus 10. So let me do that on my calculator, and I got the answer being equal to 9.26. So pKa is equal to 9.26, right? So that goes here, 9.2, okay, why is this happening? 26 plus log of the concentration of ammonia, which is 0.30 m divided by the concentration of ammonium, which is 0.36 m. And when I did that calculation, the answer I got is 9.18. Okay, so this is the pH of the buffer before anything is added, before any acid or base is added. So let me just draw a line here so as to, make a distinction between the first part and the second part of the question. Now, for the next part of the question, let me go back to the slide here. It's asking for what is the pH of after the addition of 20 mils of sodium hydroxide, 0.050 m sodium hydroxide, and 80.0 mils of the buffer solution. Okay, now in order for us to do this, what we have to do is first write down the equation for the reaction between the sodium hydroxide and the acid part of the buffer, which would be the NH4+. What we also have to do is find the moles of sodium hydroxide and the moles of the ammonium chloride that we would start off with initially. So let me go back to my writing software here. So basically, first thing I'm going to do is write down the equation for the reaction between the ammonium ion, which is the acid part of the base, of the buffer, I'm sorry, plus the hydroxide, which is added. And this is an acid-base reaction where you have the formation of NH3 plus H2O. And please note that this is not a system at equilibrium at this point. This reaction here is not an equilibrium reaction. It's an acid-base reaction which will go to completion, all right? So, actually, you know what? Let me erase this because I think I need to, I'm going to write this later on, but I think I need to calculate the moles first. So let me calculate the moles first. So the first thing I'm going to do is figure out the moles of NH3, of NH3, and that would be equal to the molarity, which is 0.30 m, multiplied by the volume, which is 0.0800 liters, because remember the question says 80.0 mils. So that, according to my calculation, will give 0.024 moles, all right? So this would be the moles of the ammonia. And I'm going to do a similar calculation for the moles of NH4+. And that is going to be equal to the molarity, which is 0.36 m, multiplied by the same volume, 0.0800 liters. And according to my calculations, this works out to be equal to 0.029 moles. Then the next step is to calculate the moles of the base added, moles of OH minus added. So that would be equal to the molarity, which is equal to 0.050 m multiplied by the volume, which is 0.0200 liters. And that would be equal to 1.0 times 10 to the minus 3 moles, all right? So those are the mole values initially in this system when the base is just added. So now I'm going to write the equation down here, which is, as I said before, the ammonium plus OH minus to give ammonia plus H2O, all right? And based on this equation, I'm going to construct my ice table. So let me scroll down a bit. So initial first, then change, then equilibrium. So the initial moles of ammonium is 0.029. For the base hydroxide, it's 1.0 times 10 to the minus 3. And then for the ammonia, it is 0.024. And we don't need to concern ourselves with the water. Okay, so what are the changes? Well, because this reaction goes to completion, then the limiting reactant would be used up. And obviously, that limiting reactant would be the hydroxide here, right? So therefore, all of it would be used up. So as far as the change of hydroxide is concerned, it's minus 1.0 times 10 to the minus 3 moles. And because of the stoichiometry, this would be the same in terms of the change, minus 1.0 times 10 to the minus 3 moles. And then over here, it's going to be plus 1.0 times 10 to the minus 3 moles. All right? So at the end of the reaction, you're going to end up with 0.028 moles here. You're going to end up with 0 moles here. And here, you're going to end up with 0.025 moles. All right? Okay, so we have the moles. The next step is, at the end of this process, after the base is added, the next step is we need to find the concentrations of each of these. So the concentration of ammonium is going to be the moles, which is 0.028. Now the question is, what's the volume? Now if you remember, the question says, let me go back to the question. The question says that you're adding 80 mils. Well, you're adding 20 mils of sodium hydroxide to 80 mils of the buffer. So that makes it a total volume of 100 mils, right? So going back to my drawing board here, the total volume here would be 100 mils, which when expressed in liters is going to be 0.1000. So let me write it here. 0.1000 liters, right? And this works out to be equal to 0.28 m. And I do a similar calculation for the ammonia. Concentration of ammonia is going to be equal to the moles, which is 0.025 moles divided by the same volume, 0.1000 liters. And according to my calculations, this will be equal to 0.25 m. All right. So far we have the concentration. So basically the next step would be to plug these values into the final pH equation, or I should say the Henderson-Hasselbalch equation. Let me scroll down here. So, okay, let me see if I can squeeze that. I should be able to fit this here. So pH would be equal to the pKa, which is 9.25. We got that from before, plus log of the base, which is the 0.25 m, divided by 0.28 m, which is the concentration of the acid. And when I did that computation, I got 9.20. All right, so this is the pH of the solution after adding the base. And if you compare that to the pH of the solution before adding the base, which is 9.18. So if you compare 9.20 minus 9.18, this gives you a change of 0.02 pH units, which is not much of a change in terms of the pH. So this is basically a demonstration of how to calculate the pH of a buffer before and after adding, in this case, a base. And there's a similar process where you could calculate the pH after adding an acid. All right. Okay, so I'm going to stop here for now. Let me see what the next topic is. The next topic, we're just going to look at some biological implications of what we discussed in terms of the pH and buffers and so on. Okay.